In the last lecture, we started parsing, which is also called syntactic processing. Parsing, we said, was probably one of the most well understood areas of language processing. Umpteen number of algorithms have been designed for obtaining the structure of a sentence, and this phase is very important because from the parse tree one then moves to the stage of semantic processing, where the semantic roles, disambiguated words, disambiguated names, co-references, all these difficult problems are solved. However, the first crucial step to all these challenging tasks is syntactic processing or parsing. So, we would like to take a detailed look at how parsing is done. Today's topic will be parsing algorithms. Last time we described top-down parsing in detail. We will mention this briefly, then move to bottom-up parsing and a very famous algorithm called chart parsing, top-down, bottom-up chart parsing. Then we will discuss what happens when a sentence is ambiguous. Multiple parses are possible for such a sentence. We described last time that parsing indeed is required, even though the meaning is more or less understood based on the word senses and their arrangements. It is still a critical task to obtain the parse tree of the sentence. That itself resolves a large amount of ambiguity. For example, if we take the sentence, I saw the boy with a ponytail. Now, with a ponytail should be attached to the boy, because it is a qualifier for the boy, and when we do this parse tree construction, the tree would reveal that the whole preposition phrase with the ponytail has this attachment with the boy. Okay. So, at the stage of syntactic processing, it is possible to find this attachment. Now, we also said that deep parsing is again a critical requirement. We took a look at one replacement test. So, I want a white horse, he wants a brown one. So, this is known as the one replacement phenomenon in language processing. One has an anaphoric reference to horse. So, these kind of phenomena need deep parse trees. We have to know the structure of the sentence in pretty good detail. So, parsing is definitely necessary. We now proceed to the algorithms for parsing, starting with the slides. We start with first a note on language modeling. Now, language modeling is a very frequently used term in natural language processing. When we use the term language modeling, we mean that a system is created for the language regularities, so that we can serve two purposes. I will write this down. Purposes of language modeling. 1. Belongingness. Is the sentence a valid sentence of the language. Question number 2, predict the next word. So, given W1, W2, W3, Wk, find Wk plus 1. So, these two are said to be the basic tasks for language modeling. So, the reason for the word modeling is that we try to capture the underlying processes of language generation and analysis and model it by means of some abstractions. Going to the slide, we look at this example sentence. Beginning of the sentence indicated by the hat symbol, the tortoise beat the hare in the race. Then there is a full stop, which is the sentence end marker. So, sentence begin marker is the hat symbol. Then we have these words, the tortoise beat the hare in the race. Full stop is the sentence ender. Now, we can see that it is possible for us to have three kinds of language models going from shallow representation to deep representation. So, the first language model is the famous or well known n-gram model. Here we simply take sequences of n words. In the current example, we show n-grams with n equal to 3. So, the first trigram or sequence of 3 words is hat, the and tortoise. The next trigram is the tortoise beat. Next, tortoise beat the. Next, beat the hare. So, we keep on collecting these 3 word sequences, okay, and that becomes our language modeling, albeit with some numbers placed beside them. These numbers are nothing but the probabilities of these trigrams. So, it is quite easy to calculate these probabilities. They can be done in multiple ways. One of the obvious ways is to see how many times does this pattern hat, the, tortoise appears in a large enough corpus and divide that count by the count of all possible trigrams in the corpus. So, this requires calculating the frequencies of individual trigrams and dividing the frequency of a particular trigram by the total number of trigrams in the corpus. So, this is a fairly useful thing to do, because it shows the surface structure of the sentence. Now, this surface structure can be captured very easily by fast processing of the text. The next representation is guided by the knowledge of language. The previous language model was simply obtained by sliding a window on the text and calculating frequencies. The next model requires knowledge of the language. So, we have two schemes here. The first is context free grammar, where the production rules are always of the form non-terminal going to non-terminal or non-terminal going to one non-terminal or a non-terminal going to a terminal. This is context free grammar. It is called context free because this kind of rewriting depends only on the non-terminal and not on anything in the neighborhood. the context in which the non-terminal appears is immaterial. So, this is the context free grammar. The next representation is called the probabilistic context free grammar, where we again have this kind of rules, but they are augmented with probability values. We will see the meaning of these probability values in the context of probabilistic context free grammar. The final representation is guided by many times the word knowledge, because we have to produce what are called semantic roles like agent, object, scene, instrument and so on. And semantic roles are always between heads first of all, and between the head and the modifier. Probabilistic dependency grammar or semantic role leveler comes with semantic roles which have probabilities associated with them. So, we find here that the language modeling goes from a very simple representation of sequence of words and their probabilities to grammatical knowledge of language, and then to knowledge of world, knowledge of language, all combined. So, this is the most sophisticated language model which can find many applications, but such language models are very challenging to create, needing as they do various kinds of disambiguation. A typical parse tree is shown here. The tortoise beat the hare in the race. Now, it is very clear from the structure as to how the phrases are composed and how do these phrases give rise to the sentence. So, here the tortoise is a noun phrase. The has the part of speech as dt, determiner. Tortoise has the part of speech as n, noun. These two together form the noun phrase, and the noun phrase is the first important constituent of a sentence. Then we move to the verb phrase component of the sentence. The verb phrase in this current example is composed of three constituents: the verb, which is beat, a noun phrase which is the hare, and a preposition phrase which is a preposition and a noun phrase. The noun phrase is the race. Now, let us understand the attachment quite carefully in this case. We see that in the race is a preposition phrase and it has a modifying role. What does it modify? In this particular case, there are two possibilities. It can be a modifier for the head in the verb phrase, namely the verb, or it can be the modifier for the hare, a hare in the race, just like a boy with a ponytail. However, the semantics or the next level of processing which uncovers the meaning of the sentence tells us that no, in the race is actually a scene for the beating activity, defeating activity. So, this should be attached to the verb phrase at the top level, thereby becoming a modifier for the verb beat. Okay. So, the tortoise is the agent of beating. Whom does it beat? It beats the hare, and in what situation? In the race. So, this is the essential piece of knowledge which uncovers the meaning of the sentence, but the crucial step in that direction is the creation of the parse tree. Now, let us understand a few more things about the parse tree itself. The sentence always starts with the start symbol S. S is the start symbol. Sentences always have noun phrase and the verb phrase. The noun phrase itself can come in many different forms. One of the forms which is shown here has determiner and noun sequence. The noun phrase also could have been a simple noun, boys for example. Okay. This is a plural noun without anything coming before it and can form the noun phrase. It is also possible that this noun phrase is composed of an article and a string of adjectives and finally, the noun. So, the little quick or the little cute tortoise. So, where little and cute are adjectives coming between the and tortoise and they will form the noun phrase. Similarly, the verb phrase again come in many different shapes. It can simply be a single verb. The tortoise sleeps for example. Okay. In this case, verb phrase has only a verb. It could also be a verb with a single noun phrase as an object. The tortoise bit the hare and there is no preposition phrase. Now, a third form is possible where the verb phrase has verb and noun phrase. However, there is a qualifier for the head of the noun phrase itself, which is the preposition phrase, and this preposition phrase gets attached to the noun phrase. Okay. All these different cases are possible and they all refer to different kinds of verbs. So, a verb which can be present singly in the verb phrase is an example of an intransitive verb. It does not take an object. A verb phrase which takes an object, but has also a preposition phrase embedded in it is an example of a verb phrase with adjunct. So, this is an adjunct. It is an additional piece of information which is not essential for the meaning of the sentence, but is providing additional information about the activity going on. So, this part is the adjunct. This is called an argument for the verb beat. Beat is a transitive verb. It always requires an object. So, this noun phrase is that essential element to complete the meaning structure of beat. Similarly, the tortoise, which is the agent of the beat activity, is also essential. Now, for a verb, all those textual elements inside the sentence which are essential to explicate the meaning of the verb are called the arguments of the verb, and the additional piece of information which comes as an adjunct is called the adjunct. It is called the adjunct. So, this preposition phrase is the adjunct. One must understand that this additional piece of information in the form of preposition phrase is not only an adjunct. So, preposition phrases need not be only adjunct. We will write an example. Here is an example. He is, so PPs are not always adjuncts. So, if you have a sentence, he is fond of horses, then fond meaning is incomplete without of and a noun phrase. All right. So, it is important to realize that preposition phrases are not always adjuncts, they can be arguments too. Fond is such an example. Fond has to take of and then a noun phrase to complete the sentential structure. Similarly, we have this example of desirous. Okay. He is desirous of something. In this case too, this of something is not an adjunct, but is essential piece of information and an argument to desirous. All right. So, we note down these points on the paper. So, text elements in the sentence can have demand words. Okay, so these are verbs, prepositions, adjectives, and so on. And then we have supply words, which can be nouns and even other demand words. So, these supply words, the supply words can be of two kinds: arguments and adjuncts. Arguments are essential for completing the sentences. Adjuncts, on the other hand, are additional information. Now, the notions of arguments and adjuncts are fundamental to any kind of parsing, be it dependency, be it probabilistic, be it constituency, does not matter. The notion of arguments and adjuncts and how they meet the desire or the akanksha of the demand words is a fundamental notion in processing of sentences to obtain their ultimate structure. We proceed with the slides. We saw the sentential structure in terms of the parse tree. Now, we show a semantic graph of the sentence. U and L here stands for Universal Networking Language. This was a representation proposed back in 1996 by an international team of NLP experts for capturing the meaning content of sentences. So, UNLs provide additional or an additional platform for capturing the semantic roles as they exist in sentences. So, many other such semantic role labeling schemes exist. Notable amongst them are FrameNet, Link Parser, the representation in Minipar parser for example, and so on. Lexical conceptual dependency is also an example in this list of semantic role levelers. One also remembers conceptual structures by SOA. Then of course, the Indian system of Karaks or case marker is an important development in the theory of capturing semantics. So, UNL comes in that line of work, and possibly the most modern entry into ways of representing semantics. So, we look at this UNL expression here. The tortoise beat the hare in the race. So, notice how the key nouns are put together to obtain the semantic graph. The beat is the most important activity in this sentence. So, this forms what is called the root of the graph or the entry node for the graph, and the agent of this beat activity is tortoise. The first argument for beat, the second argument is hare, which is the object or the patient or the theme. This is designated by many different names for beat, and then the adjunct appears as the scene where this beating of hare by tortoise takes place. This is the race. See how the content words like the verb beat, main verb beat, the noun tortoise, the noun hare, the noun race, they relate to the main verb of the sentence by different semantic relations like agent, object and scene. And this is an important point to note in the graph. The prepositions and other function words like conjunct, for example, do not normally make their presence in the semantic graph. Nouns definitely do, as does the main verb, which is possibly the most important entity in the representation. The whole graph is rooted at the main verb, and then the nouns are linked with the main verb with semantic roles. Proceeding further, we go towards discussion of the parsing algorithm. As in the last lecture, we take the simplified grammar of English, where sentence goes to noun phrase and verb phrase. Noun phrase are only of two kinds, determiner and noun, or a noun itself. Verb phrase also can be a single verb or a verb and adverb combination. So, with this simple grammar, we will proceed to discuss the parsing algorithms as was done last time. We completed top down, but let us very quickly remember what we did. We recapitulate the top down parsing. We have this example, people laugh. So, people can be both noun and verb as indicated in the dictionary or the lexicon. Laugh also can be a noun or a verb. The most of the parsing algorithms are controlled by what are called between word positions. Okay. Between the sentence beginner and the first word is the number 1, between the first word and the second word is the number 2, between the last word and the sentence ender or full stop is the position number 3. Okay. So, let us be very careful with this kind of numbering, because the parsing algorithm is controlled by these positions, these between word positions obtaining non-terminals, and these non-terminals are finally combined to produce the sentence ultimately. Now, this example sentence, if we process by top down parsing, we find that the first non-terminal symbol is S, the sentence starting symbol, and this one indicates the position of the input pointer. So, the input pointer, as it advances, the number gets incremented. First, S is expanded into noun phrase and verb phrase, input pointer does not move. So, the position remains as 1. Noun phrase is now expanded into determiner and noun, input pointer remains at 1. However, there is a backup state, noun only and verb phrase, because NP can be only a noun too, and the input pointer is at 1. Then comes the failure to match phase. There is no determiner on the input sentence, it begins with the noun people. So, DT cannot be matched. So, we throw away this particular entity, the non-terminal symbols and the input pointer combination. We discard this stack entity and bring the backup state, which is noun, verb phrase and the position of the input pointer. So, when it comes on the stack, now it is possible to match the first word in the sentence, namely people. That first word is consumed, the input pointer moves to position number 2. Now, we are expecting a verb phrase. The verb phrase is expanded to V and ADV, verb and adverb combination. The backup state is verb, input pointer at 2. Now, we match the verb laugh, and that exposes adverb. So, we would expect an adverb, but what happened is that the sentence got over. The input pointer moved to position number 3, the sentence got over, and we know that the parsing cannot be completed. Now, we bring the backup state, which is V2, and discard the adverb 3 state, and now the parsing will succeed because verb can match laugh. The sentence also finishes. There is nothing on the stack, there is nothing on the input tape. This indicates success of the parse process. Now, it is an easy matter to traverse the stack, okay, or make use of the entries in the stack, go back from the last state and produce the parse tree. This is top down parsing. Now, top down parsing is a kind of searching which is goal driven. The goal here is to finally reach a state where there is nothing on the input tape, nothing on the stack. The whole process is guided by the start symbol S giving rise to non-terminals, and the non-terminals giving rise to more non-terminals, finally consuming the data on the input sentence and stopping. However, there is this point of importance given to textual precedence. NP goes to N, it came after NP goes to DTN, which was a useless rule expansion. There is no regard for the data. We placed DT on the stack even though there was no determiner on the input tape. Why should such determiner be brought in after all? Why should we do that? Okay. So, this is completely data ignorant algorithm. There is the problem arising out of textual precedence of rules, and there are more problems like left recursion. So, if A goes to AB, then because of the very nature of top down parsing, the expansion process will go into an infinite loop. So, we move on to the bottom up parsing, and some conventions here are very useful. So, if we take the symbol N12, this means that between position 1 and 2 there is a noun, and if we take such suffixes for entities in a rule and look at a complete rule, then such a situation obtains. S1 question goes to np12 dot vp2 question means the following, that a noun phrase has been found between the position 1 and 2. The dot is to the right of this non terminal, that indicates completed work, and the dot in front of another non terminal Vp, that indicates expected work. So, we expect to find a verb phrase now, and if we find that, then the dot will move over Vp and the whole rule will be covered. The dot coming to the rightmost position in a S goes to NP-VP rule signals the completion of the parsing process. So, this dot symbol, which is also known as handle in parsing of programming languages in compiler, is an all important entity, because the dot keeps track of completed work to its left and expected work to its right. We hope to find non terminals which are to the left of the dot. No, we have already found non terminals which are to the left of the dot, and we hope to find the non terminals which are to the right of the dot. This has to be done. So, we take this example, our running example, people laugh. Let us see what goes on here. People is either a noun or a verb, and we place these non terminals n and v with the suffixes 1, 2 for them, indicating that we have found a noun between position 1 and position 2 in the sentence. We have also found a verb in position 1 and 2 in the sentence. Whether this will be useful or not is another matter. Now, having found a noun between 1 and 2, we move the dot to the right for such a rule, NP goes to n. Now, this dot shows that we have found an n, and since the dot is to the rightmost position in a rule, even the non terminal involved in the rule is also resolved. So, we have found a noun phrase between positions 1 and 2 as this dot indicates. We have also found a verb phrase between 1 and 2 as is indicated by Vp going to V12 dot. So, all these rules along with dots remain to show how much of the work has been completed, and this forms a useful knowledge for the next stage of processing. Now, if we go to the example again, we have finished this item set here. This is also called an item set. We have now decided to move forward, and here is the item set for laugh. Laugh can be noun or a verb. There is a noun between position 2 and 3, similarly a verb between position 2 and 3. So, a noun has been found, noun phrase has been found as is indicated here. We have also found a verb phrase as is indicated in this rule. Now, if we combine what has been done here at this step with the work done in the previous step, now then we can see that the task of finding a verb phrase which was waiting has been finally done, and the dot will move over Vp. So, S is the rule where dot has moved over Vp. We have seen all the words, and that indicates completion of the parse process. It is again an easy matter to consult the charts as shown in the picture, and from the chart to recover the parse tree. How shall we do it? The verb phrase goes to V. We can write it here. So, people laugh. So, we have an n here, we have a verb here also, and we have S where noun has been found, NP has been found, Vp needs to be found. And why is NP found? Because NP goes to n, the dot is after this rule. Similarly, Vp goes to V dot comes here. At LAF similar thing happens, n has been found, V has been found, again NP goes to n has been found, VP goes to V has been found, and at this stage I can finish this rule with dot moving over the VP, and this is complete. All right. Now, if I want to look at the charts and draw the tree, how will I do it? I will first develop S N P V P. So, I will write S N P V P. That is because the task of this rule, resolving this rule is done as indicated by the dot here. And then I find that the NP resolution was done in the previous chart. So, that how was that resolved? That was resolved by NP going to N, and VP going to V is in the current chart, VP going to V here, and then N goes to people, this is done in this chart, and V goes to LAF, this is in this chart. All right. So, looking at the two charts, okay, two item sets here, I can create the parse tree very easily. So, we proceed further and enumerate some of the problems with these individual algorithms. In top down parsing, left recursion is a problem. It can lead to infinite number of expansions, and in the bottom up parsing we have useless rules coming up. As I have written in the paper, there is no reason why this people, this verb for people is invoked. There is no reason why n for LAF should be invoked. Okay. So, let us combine data driven with goal driven approach. This whole procedure is data driven. We look at the words and the properties and get the non terminals. Now, we will see the top down approach to parsing and combined with bottom up strategy. So, this is the famous top down bottom up strategy for parsing, also called TDBU chart parsing, top down bottom up chart parsing. It combines advantages of top down and bottom up parsing, does not again work in case of left recursion. Left recursion removal is a standard procedure, quite easily done. We take this example, people laugh, people can be noun and verb, laugh also can be noun and verb. The grammar given is S goes to NPVP, NP goes to DTN or N, VP goes to V ADV and V. So, we apply what is called the transitive closure, idea of transitive closure. First, before we begin processing, as if there is an input pointer at 1 and we know that S goes to NPVP has to be finally resolved. So, there is a dot sitting in front of NP, and we know now that we have to do the work of finding the NP noun phrase, which again entails finding a determiner, a noun or simply a noun. Okay, any of the two possibilities can be tried or both may have to be tried. Now, this is the top down part of the top down bottom up chart parsing strategy. What is happening here is that S is expanded to NPVP, and in anticipation of future need, we also expand NP, because we have to do the work anyway. Okay. So, NP goes to DTN, NP goes to N are also brought in, and we place the dots before them, before DT, before N, thereby indicating that we have to find such entities in the text. Now, we shift to the data driven approach or the bottom up approach. So, now we know from the previous item set or the previous chart that we are looking for a determiner or we are looking for a noun. Now, the data driven approach kicks in. It says that yes, people is a noun, we have found a noun. So, NP goes to noun is now resolved, the dot moves over noun, NP is resolved. since NP is resolved, this NP in the S goes to NP VP rule is also resolved. So, the dot has moved over NP. Now, that exposes VP. So, at this stage the top down part becomes active, the top down processing becomes active. VP goes to V ADV or VP goes to V. So, V ADV we have the dot coming before verb and then adverb. Here also the dot comes before the verb, and thereby we are telling the system that we now expect a verb. It may be followed by an adverb or it may be followed by nothing, but we are expecting a verb. That work has to be done. So, you see here the combination of top down and bottom up parsing. This is the item set which illustrates this very clearly. NP goes to N, and how this has happened is that N has been matched with people, which is a bottom up strategy. Okay. And once we have resolved NP, we have resolved the NP part of S. Now, dot comes before VP and immediately the transitive closure operation kicks in. So, VP goes to dot VADV, VP goes to dot V. This is the data driven bottom up approach. When this data driven bottom up approach is over at NP goes to N, and VP is exposed with V and ADV coming, VP coming with V, that is the top down approach. I am sorry. So, bottom up and then top down. Now, again it goes into the bottom up mode, data driven mode. V is resolved with dot moving over V. Now, dot between NP and VP can go over VP and thereby obtain success by resolving S and finishing the input data items. So, this shows the bottom up data driven parsing. In the next lecture, we will take up the top down bottom up parsing and then move on to probabilistic parsing, just start probabilistic parsing.